Okay, let's get started. Today it's our great pleasure to have Yaron Lipman from Weizmann and Facebook AI Research giving a talk. So we will also have two panelists, Vincent Stiefman from MIT. Actually, he will start at MIT as a system professor next year. That's congrats. And we also have Toga Vital from Stanford. Okay. Okay, so the format is that as usual, so Yaron will give a talk for 1 hour, then we'll have a panel discussion among all of us, right? So Yaron has done a lot of work at the intersection of graphics, machine learning. So today he will talk about unifying implicit neural representations. So without further ado, let's welcome.
Thank you. So let me start by thanking the organizers and also the panelists for taking the time and making this thing happen. I think it's a great service to the community. And I hope I'll do my part reasonably well. So I'm going to talk about work that I've been doing during my sabbatical. I'm currently at Facebook AI, sabbatical from Weizmann Institute of Science. And I want to take the opportunity to do something slightly different than usual. I'm going to talk only about a single work, but I will try to dive into the details. And hopefully I will be able to kind of explain the technical details in a relatively intuitive way, and hopefully to also steer a discussion afterwards with our great panelists. I might use a little bit less than 1 hour or 50 minutes. We'll see how it goes. Okay, so just one motivation slide. So the motivation of this work, which is pretty similar to other works we've seen in our space, is learning the geometry from raw partial data. Usually when we say raw partial data, we mean one of two things: either geometric data, like shown here on the left-hand side, or images of three-dimensional scenes. In this talk, I'm concentrate on the geometric data, meaning that we get some sort of a noisy point cloud that comes from rate scan or extracted from images, or a three-dimensional scan, partial with holes and noise, or so on. To make things really concrete and well-defined, we're going to kind of focus on the following scenarios. So the input to our problem would be a bunch of three-dimensional points floating in space, denoted xi. And our goal is to reconstruct a surface S that passes through the points and has some plausible shape. This is a well-known problem. Many people have worked on it before the deep learning area, and I'm going to mention a little bit about that as we go along. It's called surface reconstruction. Now, when someone tried to develop an algorithm for surface reconstruction, I think that the first thing that he chooses is the way he wants to represent the end product, the surface. And as the title of my talk kind of hints, the representation that we're going to choose is the implicit representation. What does it mean? It means that we're going to represent our surface as the zero level set of some unknown function u. So all the point x which lie on the zero level set of u will define the surface. And mathematically, in order for this definition to really define a surface, we can use something like the implicit function theorem, which says that if at every point where u vanishes, it also has non-vanishing gradient, then locally the zero level set looks like a graph, which means that globally it's like a manifold or a surface. So we're going to use implicit representation. However, when we actually try to do that, we see there is another degree of freedom. So we only care about the zero crossing of the function u, but clearly outside the zero, where it's say negative or positive, there is a lot of degrees of freedom that we can play with. Two ways to set these degrees of freedom, and which are also popular in the literature, are occupancy function and sign distance function. So in occupancy function, basically we define the interior of our object to be to get 1, a little bit like an indicator function. So the inside of our object is 1 and the outside is 0, and the surface is defined as the interface, this interface between 0 and 1. So this function is defined here as a discontinuous function, which already a little bit hints about the problems with this definition. In practice, what people usually do, and also what we're going to do in the next slides, is we actually work with smooth or continuous functions which have a sharp transition area near the surface. However, this has one drawback of this representation, which I think it's important to note early on, is that when you work with occupancy function, the level set tends to concentrate near the surface. And this have some numerical issues. For example, if you want to contour the surface, you want to extract the three-dimensional surface using marching cubes or something like, you sometimes can get quantization effects or something like that because your surface basically is constant far away, even a little bit off the surface. So that's occupancy function. A more elaborate representation, but of course costlier, is the sign distance function, which in addition to indicating whether you're outside or inside the surface, it also encodes the distance of every point. So for example, this point, we're going to encode the positive distance to the surface, and at this point, we're going to encode the negative distance to the surface. Again, the choice of whether we take positive or negative inside or outside is obviously arbitrary. So it is written here, basically the sign, whether we're inside or outside, times the distance to the surface. Now I want to spend one slide about classical surface reconstruction. So I would say, again, what I'm saying here is kind of a gross generalization and an oversimplification of a huge amount of literature on surface reconstruction. And I'm only going to talk about a little bit of those works and only on those who work with implicit functions. Okay, so please excuse me if I forget a lot of things, but at least my take on the situation is as follows. When in classical algorithm, when people came to reconstruct surfaces from point cloud, say, they usually chose as the implicit function a parametric model from a linear or a convex space. So we take a bunch of basis functions and we only look for linear combinations of those functions to represent the implicit. I think this drove the research into looking into convex kind of algorithms for surface reconstruction. And this is something that in some sense deep learning freed us from, which I'm going to mention in a second. For example, these 4 or 5 works, which are kind of classical, all of them use linear basis functions, whether it's Kashdan's Poisson surface reconstruction, which use grids values, or Zhao et al. Also use grids values, and radial basis functions are not grids, but are linear spaces of function, linear combination of radial basis functions, or piecewise polynomials in those MPU's papers. Not all these works work with convex loss energy, but since our function space is linear, there is a good incentive of trying to get the convex loss, which will end up with a convex or even a linear algorithm, and of course, all the benefits that come with it. In recent years, we've seen really an explosion of works that chose for this U a neural network. Now, a neural network is also a parametric space of functions, but it's not linear in the sense that there's no linear relations between the different function members and the parameters. And this means that even if we work with convex losses for reconstruction, as was used before, like Poisson reconstruction, we still end up with a non-convex problem. So in that sense, it kind of freed us from the necessity of looking for a convex formulation. And indeed, many, many interesting and wonderful works have appeared in this space, working with non-convex functionals. And I would say that basically half of those kind of work with occupancy functions and half with SDF, each kind of injecting a different kind of inductive bias into their solutions. Now, if I try to kind of say, like in general, how these INRs implicit neural representation are being trained from raw data, I think that mostly they can fit into the following mold. The loss is usually a sum of two things. One term is, we can call it a data term, which basically kind of pushes the zero level set to pass near or at the data points. So we just want the neural network to be zero at the data points. And the second term, which we can call a regularization term, kind of makes everything smooth elsewhere or plausible elsewhere. Now, the main issue about this kind of design, which generally works well, but still there are some issues, and the issues are usually that when we're combining different losses, we not often knows exactly how the minimizer look like. So, for example, when we combine two losses, is the data term guaranteed to be satisfied? So our surface needs to pass through the points. Is the regularization well posed, or there are many local minimas? And maybe the sum of the two terms would yield a new local minimas which are undesirable. So all these questions are, I think, very important when we come to design losses for training INRs. And this is exactly the point which I want to focus in this talk. As one motivating example, here's a phenomenon that you can all try and see for yourself. So if you take only point constraints, so no normals has a stronger regularization effect in INRs. So let's just take a bunch of points, and now we're going to train a sign distance function, and we're also going to add positional encoding using those Fourier features. So what often happens is that this kind of introduces a sort of kind of inductive bias into this loss, and we often get extraneous surface part appearing in the scene, either floating around or connecting things, and you can even kind of see those high frequency artifacts in those added parts. On the other hand, on the right hand side, that's the loss which I will try to advocate in this talk. It's not perfect as well. I'll mention its problem later on, but at least as far as those things, it will improve over in the situation because it has an inductive bias which strives for minimal surface area. So I would try to make the argument that minimal surface area is an inductive bias we would like to incorporate in a loss, and I will try to explain how we can do that. So the goal of my talk would be to introduce a loss or a family of losses that we can say something about the minima, and they have certain desired properties. I mean, inductive bias, by that I mean the minimizer of these losses have some properties that we'd like to have when we reconstruct surfaces. As it happens to be, this type of loss necessarily kind of as a byproduct or as a reason also unifies between the sign distance function representation and the occupancy function representation. So to kind of design this loss, so I have one slide which kind of dives a little bit more about what is the end product of this talk. So the product is a loss which I would like to call a phase loss. The name will be clear as we move along. It will also have the form of a sum of two losses, a data loss and a regularization loss. And it will be a one parameter family. I'm doing like a small disclaimer. At the end, I'm going to add a little bit, one more term to it, but at least the theoretical part is going to analyze a one parameter family version of that loss. So that parameter is called epsilon. As epsilon goes to 0, we can prove several stuff about the minimizers. We can show that it converges to a proper occupancy function. The minimizer U of this loss converges to a proper occupancy function. The zero level set guaranteed to pass near the data points as minimizes the surface area, and there is a certain log transform of this occupancy, which is a smooth version of sign distance function. So to kind of visualize all these properties, you can look at the right hand side. So what you see here is the minimizer of this loss, where the input here, I don't know if it's clear, but the input are like 4 points at the corners, at the vertices of this pentagon. So these white points here are the xi that I mentioned before. When you minimize the loss, this is how the minimizer looks like. So red is 0 and blue is 1. And you see that it's not exactly occupancy because epsilon is not 0, it's like 0.01 here, but the level set are already kind of dense around the 0 level set, which is shown here in black. So this is the level set. So this is approximate occupancy. It also passes near the points, as you see here. And it has a minimal area. You can kind of appreciate that by the fact that these lines are straight. And the logarithm of this function, shown here on the right, approximate the sign distance function. It's a smooth version. It's a viscosity solution of the diagonal equation. I'm going to explain about that in a second, but you can already appreciate that it looks a little bit like a sign distance function. Okay, so that's the goal of this talk. And now, basically, I could just give the formulas and jump to results. But again, as I said, my goal in this talk is really to go into details. Hopefully, it will steer some discussion afterwards, which will be interesting to the participants. So to kind of motivate the loss, we're going to do a quick detour. And I'm going to spend the several next slides to introduce a physical variational problem called phase transitions. And this will give us the mathematical tools to define the phase loss for INI training. So what is phase transitions? Phase transition deals with the physical problem of having a container, which is denoted by omega. And in the container, we have two mixed fluids. Let's call it the yellow fluid and the green fluid. And what we're interested in to understand the equilibrium state of these two fluids. What happens after we don't touch the system and let it rest? How do these fluids arrange themselves inside the container? The high-level motivation is that in physics, they usually arrange themselves so that the interface between the two fluids has minimal area. And from that part, we're going to take out this component of minimal area and use it for surface reconstruction. Okay, so the next step is how do we mathematically represent this situation? So we're going to represent it as a density function U, namely an occupancy. This is going to be our occupancy in the near future, which represent the density of, let's say, the first fluid. Okay, so the yellow fluid. So at every point in the domain, U says how much yellow fluid we have at that point. Another constraint which comes from the physical problem is the fact that the container is closed, so no materials, no fluid is coming in or leaking out of this thing. So the total mass or amount of first fluid and also the second fluid are constant. So the integral of U equals some constant m between 0 and 1. Of course, having either 0 or 1 is not interesting because if we only have one fluid inside, then there's nothing interesting happening. And now phase transition basically models the situation of the two fluids by formulating an optimization problem, a variational problem. This is due to Gurtin in 1985. And basically, the way it's represented as among all the function, the density function from omega to 0, 1, which have a constant mass of the first fluid, we want to achieve the one which minimizes an energy. And the energy is basically, there is some scalar function W, which is a double well potential. And for each point, we're going to measure W of U. Let me break it down real quick. So W has a form which looks like this. It's double well potential in the sense that it has two global minimas at 0 and 1, and elsewhere it's positive. That's pretty much everything we need to know about this function. Of course, the name comes from the kind of the way this image looks like. It has two wells. And basically, if you think about it, what W of U is trying to do is to force every point in the interior to choose a side, either 0, fluid number 1, or 1, fluid number 2. But not all points have to decide. Some can be a little bit of fluid 0, a little bit of fluid 1, and so on. Now, this formulation looks nice, but it suffers from the ill-posedness problem that I mentioned a few slides ago. Let me kind of try to explain that. So think, for example, about the following situation. Consider a function that for each point in the container fixes exactly one of the two numbers are either 0 or 1. So this is a discontinuous function. It just says at this point we have fluid yellow, or at this point we have a fluid green, and that's it. Now, if we decompose our domain such that the volume of the yellow part is M, then we have a global minimum of this problem, right? Because the loss will be 0. Okay, assuming that the W here is 0. I didn't mark that, sorry. So here I'll do it now. This is the zero value. So basically any decomposition of the space such that the yellow part has the volume M gives a global minimum. So clearly this is the general problem. It has too many global minimas. It enforces nothing about the interface between the liquids, and it has no physical meaning. One thing that the small change which makes this a physical system and provides all the nice property we want is a small perturbation with the squared norm of the gradient. This famous Dirichlet regularizer, we added times some small epsilon. So that blurs a little bit the image. So you can see here now we don't have like a clear kind of interface between the two liquids. They can blend a little bit, but it stabilized everything. It produces some regularization on the interface. This theory is called van der Waals-Kahn-Hillard, or WCH in short. And this is the final formulation. And the interesting thing about this theorem, about this theory, is that it says that as epsilon goes to 0, this optimization problem in some well-defined sense gets close to a limit optimization problem. So what is the limit optimization problem? In the limit optimization problem, we have a function, again, in this discrete setting. For each point in omega, it prescribes either fluid 1 or fluid 2. And among all these decomposition that satisfy the mass constraint, it looks for the one that minimizes the interface area. Okay? There is some constant here, which does not matter for the minimizer of this thing, of course, but it does matter in order to show convergence. So the value of the functional, for the value of the functional to be the same in the limit, there is some constant here that has to be taken into account. Anyway, so the mathematical statement, which actually uses some theory which preceded this, this physical interpretation, is that if you think about the functions that represent this optimization problem, which we call E epsilon, and we call this limit or the second optimization problem E0, then basically there's a theorem that says that this optimization problem E epsilon converges to E naught as epsilon goes to 0. Okay. Now this gamma convergence is a convergence of functionals. It's a little bit more intricate than just simple convergence of functions or numbers. I won't get into too much details here, but I do want to say, what does it imply, this gamma convergence? So the gamma convergence would say that as epsilon gets smaller and smaller, the minimizers of this problem here will enjoy two properties. The first property is that they will get closer and closer to a proper occupancy, namely every point will choose either 0 or 1. Again, for a prescribed epsilon, it will be smooth, but as epsilon goes to smaller, this interface, this blurry interface here, will go and become thinner and thinner until it will, as epsilon goes to 0, it will disappear. And the interface, this 0 level set S, will have minimal surface area. So that's the implication of this theorem of the functional, and what our plan is to use that for training implicit neural representations. So let's go back to the surface reconstruction scenario. So in the surface reconstruction scenario, we have input points floating around in space. So the first thing that we want to do is think about this thing inside some container. So let's imagine some bounding box omega around those points, and this is the omega that we're going to work in. As the density of the first fluid, there's a very natural choice here, as I indicated before. We can basically take an occupancy function, right? So at every point in omega, we're going to put some value between 0 and 1, which indicates how likely are we inside the shape, right? Or what is the density of the shape at that point. And now, let's think about the optimization problem. So the functional here that we minimize is the part that is responsible for converging to a minimal surface area occupancy function. So we want to keep that. However, this part, this global thing, is really a problem specific. It comes from the fact that we have a physical system and we have a fixed amount of fluids. So the problem here is that we don't know what is the mass of the surface that we want to reconstruct, and that's not what interests us. What we actually want to use, we want to use the constraints in order to make sure that our zero level set passes through the points, right? So let's do something which sounds reasonable for this thing. We're going to replace these global mass constraints with many local ones. So imagine that you put a small ball around each input point. We call these balls BI. And now we want to say that the average of the density of the insideness liquid fluid at that ball equals half, all right? Now, if the theory will hold also in this case, and U will become closer and closer to a proper occupancy, mainly almost every point will choose either 0 and 1, then if the average equals half, it will necessarily mean that they're both values 1 and value 0 at the vicinity inside this ball. And this means that the level set will necessarily pass through this ball. So note that this is slightly stronger than what we usually do in INRs. We're not only asking that the value will zero out at the point, because if the value zero out, it does not mean that it necessarily crosses the zero. You know, if you think about y equals x squared, then you can get to 0 without crossing it. But this condition will force the zero level set to pass there, to change from positive to negative, from zero to go from above half to below half. So it will force the half level set of this occupancy function to pass in those balls. But still, this is not really usable for training INRs, because these are hard constraints, and we don't know really how to incorporate many hard constraints in deep learning. So we'll do what everybody does. We're going to change this thing to a soft constraint, meaning we're going to replace the hard constraint with a sum that goes over all the points and kind of quantifies the deviation from the averages in these balls to equal half. And we're going to add this term with some coefficients in the function. And we end up with an unconstrained energy. And this is energy we can optimize. We have a new, we paid by adding a new parameter lambda. So we have now both lambda and epsilon, but at least we don't have hard constraints. This is an unconstrained problem. Okay, so here's the problem we ended up with. We call it f of epsilon. And here's what we hope to get as the limit problem. So the limit problem would be, again, minimizing every point to be either inside or outside the shape, minimizing the interface area between 0 and 1, and making sure that the interface passes in the vicinity of every input point. And what we prove in this paper is that if we make sure that lambda goes to 0 with epsilon, but not as quickly as epsilon. So in particular, this is an example of instantiation of the theorem, actually. So if lambda should behave like epsilon to the power of something between 1/4 and 1/2, so let's say 1/3. So it goes to 0 with epsilon, but asymptotically slower. Then the functionals f epsilon would gamma converge to f naught as epsilon goes to 0. The practical implication of that, as I said before, would be that as epsilon goes to 0, the minimizer are proper occupancy functions, meaning every point will choose whether it's inside or outside the shape. The interface will have minimal area. So these two properties are inherited from the phase transition. And the new part that is added for the surface reconstruction is that the interfaces will be guaranteed to pass near the input points xi. Here's a two-dimensional visualization of the situation. So here I optimized the phase loss on the white input points. I hope you can see that, I don't know, the points are here, for example, and here, this is in the Koch snowflake are here. And in this Gecko two-dimensional images, there's a lot of points. You see this white line here. So what you see here is basically the U that optimizes. You can appreciate the fact that it is closed, but not exact occupancy. And it seems that it kind of enjoys this minimal surface area because we don't see any extraneous parts popping out. I want to give a quick intuition to how the gradient norm and the area are related. Because we added gradient norm of something and we said something about area. Now the proof of this gamma convergence, to be honest, is pretty delicate and not trivial. However, I think just to understand how gradient norm is related to area is something which is something that I can try to illustrate relatively quickly, and I think it's useful. So let's see that. So there is a formula that is called the Coarea Formula. And it says basically that if we have a function which is differentiable and we integrate its gradient norm, then in some sense, a little bit like Fubini theorem or stuff like that, we can write it down as integral over the level sets. So we integrate over the level set, and for each level set, we integrate over the level set. So it's kind of a decomposition to different axes. So this is the simplest version of this formula. So the integral of the gradient norm would be the integral over all the scalar which correspond to level sets, and then the integrand would be the area of that level set. So imagine here on the right that you have this function u, which is an occupancy function of this Koch snowflake, and what I show here is actually the level sets. Now, since the image of U is only between 0 and 1. There's no other level sets outside that space. This thing equals the integral between 0 and 1. And now, if we approximate this integral with the rectangle rule, so we take 0 and 1 and we divide it to equi-space with n points, actually n minus 1 points. And now we approximate this integral with the rectangle rule. So this is basically the area of this level set times 1 over n. So in some sense, the rectangle rule would be the average of all the areas of the level sets between 0 and 1. Now, if you look at the right image here, since we're close to occupancy, most of the level set will be concentrated around the 0 level set, right? So we're taking an average of a lot of things, but most of them are concentrated around the black line. So this thing would approximate the area of the black line. So in that sense, regularizing the gradient of the ambient function u controls the area of the 0 level set. Okay, there's one piece of thing that we haven't done yet, and this is talking about the W function. So all the theory that I've mentioned thus far works with pretty much any W function that satisfies those basic properties of being positive, maybe a little bit of regularity, but not much, and two global minimas at 0 and at 1. Okay. So all these functions will do for the theory. So there's a degree of freedom here that we can use. So let's do that. Let's choose a W which give us something extra in this representation. And this is where the sign distance functions comes in. All the parts till this point was about occupancy function. So what I would like to say is that if we choose W in this way, so this is basically, I'll just break it down. So it's W of S is S squared minus the ReLU. So I usually mark with this subscript plus the ReLU of a function. So max between 0 and 2s minus 1. So actually, this is the graph of this function. Okay, so this is nothing too special. And now once we have this function in place, consider the minimizer u of our functional, and define a function w, which is a log transform of this function. So it looks a little bit ugly, but in a second I will make it a little bit clearer. So w is square root of epsilon of the logarithm of either 2 minus 2u or the logarithm of 2u, depending whether we're inside or outside the shape. If we're inside the shape, density greater or equal to half, then w would be negative. And again, this is arbitrary choice, but we just make it. And if we're outside the shape, meaning the density is smaller than half, then this thing would be positive, the distance function. And now what we want to claim is that if we look outside those balls where we constrain some stuff, and we look at area where w does not vanish, then w can give an interpretation of its own, characterization of its own. It is a solution to a PDE, which looks like this. So let's again try to break it down. What do we see here? We see something small, square root of epsilon multiplying the Laplacian. We have sign, which we can ignore for now. And we have the iconal here. This is the iconal. The iconal equation, for those who don't know, it's the norm of the gradient of a function equals 1, or the squared norm equals 1. This is basically the differential equation that governs sign distance function. So what we have here is a sign distance function PDE with a smooth perturbation, a Laplacian. This type of equation is known as a viscosity version of the iconal equation, and it gives a smooth SDFs. All right. So the version that it gives is a smooth version of the SDF, and it is known that under some conditions, as epsilon goes to 0, this converges to the SDF. Okay. So basically, by choosing, let me just sum up this result. By choosing this energy density W, we get that the log of our occupancy behaves like an SDF. Okay. I want to again give a little bit intuition to this result, because this log is so it's a little bit, maybe it looks like a little bit of not clear where this thing comes from. So this comes from for a very classical thing that people used in many different situations before, and I just want to highlight that. So just to make things concrete and concise, let's consider just area where W is positive. So we are actually, let's say, outside the shape, like shown here, this O. So when W is positive and we're outside the shape, then the density is smaller than half. We look at our energy. So now we plug in, instead of W, this chosen W that we're discussing here. So U squared minus the positive part of 2U minus 1. And since U is smaller than half, 2U is smaller than 1. So 2U minus 1 is smaller than 0. So actually, this thing is canceled, right? So we end up with this thing. Now, note that I also removed this positional constraint. Why? Because I'm looking now outside the domain. What I want to claim is that the minimizer of F epsilon, if I look at some domain outside those balls, then it's also going to be a minimizer of this problem. Why do I say that? Because if I find a local variation of this problem of the function u, I can change the function u inside O, which makes this integral smaller, then the same variation would make this integral smaller. So it's not a minimizer anymore. So what I want to say is, what I claim is that the minimizer of this has to be a minimizer of this. And now we end up with a relatively simple variational problem. And there's always, with every variational problem, there's come a PDE that characterizes its minima. So the minimizer of this variational problem, so you know the U squared contribute U, pretty much like a derivative, and the gradient square contributes the Laplacian. That's something which is well known. So basically, the minimizer satisfies this equation. It's basically an eigenfunction of the Laplacian. And now a classical result and a trick, which has been used many times and can be found in also in classical PDE books, is that if you take this linear equation, so this is a linear equation with the Laplacian, and you transform it with a logarithm, then you're solving a semi-linear equation with a Laplacian and iconal term. Okay, this is not, I didn't invent that. That's something which is well known, exists in many places, and it's very useful. People have used it also in computer vision many years ago to work with SDFs. Another interesting, so basically, let me recap. If we look at the solution of this eigenvector problem to the Laplacian and we do the logarithm, we get something that behaves like a smooth SDF or the distance function. Some of you may recognize this result also in the context of Varadan, which basically relates between heat kernels and distance functional manifolds. And indeed, he actually formulates his theorem exactly like this, maybe for more general Laplacians because he works on manifolds, but it also works in obviously in Euclidean cases. And basically, his result deals with the logarithm of heat kernel, but it has this formulation as well. If you look at some domain and the boundary of the domain is half, again, I tweaked a little bit with the numbers so it will match what I'm doing here. Everything is a linear transformation of everything else between what I'm writing here and what he has in the original theorem. So if at the boundary we have half, then as epsilon goes to 0, this converges to a distance function. Now I want to highlight that this convergence, if we want to rigorously prove that we converge to the sign distance function, it will be hard because we have these balls here and they kind of deviate the boundary condition inside those areas. So this part of the theory is not closed. I wasn't able to show that there's actually convergence to sign distance function, but only that outside the balls we satisfy the viscosity equation, which kind of is a perturbation of the sign distance function. Okay. Here how it looks. So this, we've seen these three before, and here at the top we now see the W. So you see that it looks like a sign distance function, but it looks smoother, right? It does look a little bit smoother than sign distance function. In order to appreciate the difference, let's go back to this pentagon example. So again, the input here was five points of the vertices. And this is the minimizer of this U function. And this is the W at the middle. That's the logarithm transformation. And on the right, I'm visualizing the deviation of the gradient norm from 1 in absolute value. And what we can see here is that this thing kind of have higher values at these lines that go from the points to the center, at the center definitely, and also at the points themselves. And I want to explain these things. So first of all, the iconal equation, which is gradient of U equal 1, does not have a smooth solution. How do I know that? Because let's assume it had a smooth solution and look, for example, at the center of this pentagon. This center of the pentagon, because of symmetry, it has to be something like local minima or global minima of the sign distance function. All right. So if the function is differentiable, the gradient has to be 0, but we said it satisfied gradient equal 1. So this is a contradiction, meaning there's no differentiable solutions to the SDF in this case. So in the center, we have to be smooth. So this kind of explains the deviation in the center. To explain the deviation at those kind of tentacles going from the center to the points, you can think about the lines that go from the center. So these are the medial axis. I don't know if all the listeners knows what are the medial axis, but these are points where the gradient is discontinuous in the SDF. Why is it discontinuous? Because when I move a little bit to the left, the closest point is here, and move a little bit to right, the closest point is here. So there's a jump. So there's a jump. There's a non-unique closest point. So the gradient jumps between the two sides of the red lines. Okay, so again, we cannot approximate with a smooth function a discontinuous gradient. So again, here we have a smoothing of the gradient in that area, and for that comes the loss. And the last thing is that we have high error at the points, and the high error at the points comes from the fact that we're taking those circles and asking an additional constraint which kind of deviates. Now the Euler-Lagrange equation are no longer this viscosity iconal. It's something, there's something extra, and therefore it's going to deviate from that. So motivated by this area, we, in a practical kind of way, we decided it's a good idea to add also at the points themselves something which encourage a better SDF reconstruction. So either if the normals are not known, we're adding something like the iconal, so asking that the gradient of W, which is the SDF version, the norm equal 1, or if the normals are known, which is also a typical case, we ask that the gradient of W would equal Ni, which is both incorporating the information of the direction of the normal and the length of the normal. So this is deviates a little bit from the theory that I presented. I've been adding this part of the loss at the points themselves in order to incorporate a better solution at those balls that we've taken out. So here's how it looks. So I think this is an interesting slide. So here, basically, we see the same input points. Again, it's not very clear, but I'm gonna I'll draw the points in purple. So these are the points I'm gonna highlight. So these are points taken from more or less half a circle. On the left, I'm showing the result of this iconal regularization shown in Grop et al. So we only normalized the gradient of some function to be of norm 1 everywhere. So that's the formulation. And this is the result we get. So there is some smooth continuation to almost a perfect circle. Again, this is an SDF learning. On the center, I'm showing the phase without this new part, like mu equals 0. That's the first part I was discussing. And you can see that still it looks like an SDF, a smoother one. But we can clearly see the minimal surface bias. So we see that this thing cuts here, and the lines are more straight at the points. On the right, I'm showing also with the gradient norm constraint at the points, and it's not like the best result, but you can kind of appreciate the fact that the results are more kind of regular near the points, which actually in 2D, it doesn't make a big difference, but in 3D, it makes a huge difference. So incorporate this thing in 3D makes much better reconstructions. Okay. All right, I'm almost done. A bit of standard qualitative experiments. This is the benchmark of Williams et al. From 2019. This actually the result. I took the results for all the methods except the phase from this NSP paper, which is not a proper. It's not a proper INR. It's basically a kernel method based on kind of motivated by deep learning, I would say, which does produce nice results. And basically, the phase compared favorably to all these methods. I think the main point here. This is these data sets. Oops, sorry, mistake. These data sets use both points and normals. And I think if I have to point to one thing which works in favor of phase is the fact of this minimal surface property that kind of clears some of the artifacts that other method adds. I think an interesting experiment is in the context of this fast learning of INRs when we use Fourier features. If you use Fourier feature only with points, I kind of hinted that at the beginning, you tend to get a lot of artifacts added, like shown here. These are rectified in using phase, although not completely. So here's a failure case of phase. We still have a bunch of extraneous surface left, but in general, it improves situation. This lower surface area does show in many results. So I would encourage people to use also this surface area inductive bias when they use high frequency learning. Actually, it also works for Fourier features or Siren as well, Vincent and so on. Okay. All right, these are just large point clouds. taken from the Stanford 3D repository and Sitzman, Vincent Siren paper. Yeah, nothing to add here too much. I think just qualitative results. Let me conclude real quick. So some drawbacks. The additional losses I've talked about are not included in the theory. I think that's interesting future work. The local constraint, I only described balls, but this is also a degree of freedom. We can take a more general integrals of weights function. We can maybe learn them. I think that's an interesting follow-up direction. Practically, I think one important takeaway from this talk is that with a single INR, you can combine both occupancy and SDF with this slope transform, and then you can add losses to whatever you want. If you want minimal area, you do it on the occupancy. If you want something else, do it on the SDF part. So these can be trained simultaneously. And I want to end up with something which I perceive as a big, huge drawback of this method. I think quality-wise, we get very close to surface reconstruction classical algorithm. Maybe we surpass them with the ability of learning collections and so on. But the speed of training a single model is way, way slower than classical methods. Either using some encoder framework or faster training. I think it has to happen in order for this thing to really be usable for surface reconstruction. Thank you very much, and I'm happy to hear any questions.
Okay, thank you, Yaron, for the wonderful talk. Then we'll follow this will be followed by a panel discussion among what Yaron has talked about, and also all the relevant stuff. Okay, so if we have missed the beginning of this seminar, so we have two panelists. Vincent Lipman from MIT, so he will join MIT next year, right? So as an assistant professor, he has done many works in near-scene rendering, representations, and also implicit. Okay. In fact, one of the works was cited in Yaron's talk. Okay. So we also have Tolga Feldman from Stanford. So he's working in the area of geometry learning and so on. Okay. Okay. So let's start with maybe questions from panelists. Maybe start with Vincent, since this is close to what you have done in the past. Okay, we cannot hear you. Vincent, so.
Yeah.
Okay.
Can you hear me now?
Yeah.
Okay, great. Sorry. Fantastic talk. Also beautiful slides, Yaron. I have to get some inspiration from that. One thing that I was wondering is, for one, I really think this is like an important thing to have this minimal surface solution. You showed the Siren example in the Siren rooms environment. This was actually something we had to deal with like an additional loss to make sure that in the center of the room there wouldn't be like an extraneous sphere basically floating in the room. Then we had to actually regularize that to get rid of that, which was very awkward. And I think this is like a very nice and principled way of dealing with this. One thing that I was wondering is, you mentioned that there are still some artifacts in one of the scenes when you reconstructed them. I wonder why is that? Is that because basically the local constraint, which is the integral over the local balls, is that hard to enforce? Is that the problem, or why do you think that actually happens?
Yeah, great question. In the sense that it's a really good question, because I don't know the answer. To be honest, I don't know. It's not the fact that these spheres are hard to enforce. These are really small spheres. They're not on the scale of this thing. So that's not that. It could be that I stopped the training too early. Theoretically, we know that these Fourier features keep the thing still universal. So the minimum and also the local minimum should have a sort of a minimal surface. So the honest answer is that I don't know. But it's a good question. Yeah, I don't know, to be honest. Yeah.
Yeah, I think that's super interesting. I really appreciated the perspective of saying that you force the to integrate over these little balls and forcing the Well, doesn't matter. I forgot it already, but it was cool. That is a great idea.
You mean the level set to cross? So the
Yeah, exactly. Exactly. Like constraining the integral over the ball to make the level set cross through the ball. That is really cool. I like that a lot.
Let me just say one thing. So sometimes minimal, I'm not sure this is the case here, but sometimes minimal surface has this property that it's not what we expect. For example, maybe the minimal surface constraint here would complete the area between two legs. And then it caught in that local minima, and there is like putting a tent over that thing. Although it doesn't look like this here exactly, so I'm not sure this is a good answer, but I'm just saying that the minimal surface is good, but it's not always good. It can have a minimal surfaces which are not desirable.
That's really cool. So this is, I think, so one thing maybe that I think is also kind of worth discussing is this problem that we're facing, that we are, training these things with stochastic gradient descent, and we are, especially when we fit these surfaces, basically relying on sampling points over the surface. But of course, especially for large scale scenes, it gets hard. It's actually an interesting problem to ask, where should we sample, especially to enforce the regularizers? Where in space do we sample? How do we pick these points? How do we make sure that that does the right thing? So for instance, in the Siren, in the rooms environment, some things that we tried is actually starting enforcing the regularizers close to the level sets, to the zero level set of the function, where we're basically injecting information in terms of the actual training points that we are observing, and then trying to enforce the regularizers in an increasing distance away from the surfaces. And that kind of worked, but it also wasn't a great, didn't lead to the desired results. And I think this is actually kind of a big downside, that because these things are pretty hard, pretty expensive to evaluate, we are constrained in how many points we can sample. And therefore, this is actually a problem we have to think about.
Yeah, so I completely agree. So I just want to, so again, I don't know the answer. I just want to say that choosing the sampling is a little bit like adding in the loss a weight term, right? Which kind of favors areas on other areas. And sometimes this weight can be chosen in a way which emphasize area where the error is larger. One thing which I can say, which might be related to what you're saying, is that it's related to the fact that the sign distance function have discontinuous gradients. Mm-hmm. And I think that the inductive bias we have when we train MLPs out of the box is of smoothness, and this can create a kind of bad Gibbs-like approximation problems near these areas where this medial axis, where the discontinuity of the gradient. So maybe these areas are important. Maybe going to a viscous solution of SDF would be better, more stable, but just my 2 cents on that.
Why actually, if I ask, like, why, I think it's really cool to relate the occupancy function, the sign distance function. Where do you kind of see, do you see like a value in having both of these around? Because it seems like, as you said, the sign distance function is by design has strictly more information than the occupancy function, I guess. So is that, do you see advantages of keeping the occupancy function around as well?
So I think, at least in the context of what I presented, the occupancy function is important if you want to add this minimal surface kind of. So the minimal surface is easier with the occupancy. The gradient, the contouring, projection, also things like intersecting array, it's easier with an SDF. So I still think that both of them are useful. So I think that you can train an SDF, and now you can also do the inverse transform and add this like minimal surface energy to that part. So you can train both SDF and minimal surface if you want that. So so I think the related slide would be this thing, right? All of these solutions are perfect because all of them are sign distance function and pass through the points. So the question is, what kind of inductive bias you want to enter your system? You want to have low curvature surfaces, or you want to have minimal surfaces? this would be like low curvature, and this would be minimal surface. And maybe there are other things that you or other people can think about that you wanted from the.
Okay. Thanks, Vincent, for the questions. Thanks, Yaron, for the answers. So next we'll go to Toga.
Yeah. Thanks, Yaron, for this great talk. I really enjoyed it. There are a lot of new insights and novel perspectives here. I think I'm really excited about the future work that this can actually bring. And on that exactly, you had a lot of earlier works on unsigned fields on point clouds, right? And I'm wondering if this can also go to an unsigned case, if it can also cover.
That's a good question. So all the things that I mentioned about this viscosity solution and people that were converging to distance, these actually work with distance function. The fact that we multiplied it by minus from the other side, that's kind of an addition. So definitely, if you want to do something with viscous solution to distance function, that also I think works as well. Regarding the area of the interface, I'm not sure. I'm not sure because at least it's not clear to me how you can work with unsigned distance, because for unsigned distance function you don't have per se manifold of crossing.
Right. Exactly.
In that sense, it's more general. Yeah.
It's probably one of these. Yeah. Maybe special cases somehow, or edge cases of that. Yeah, it would be interesting to see that. And because usually we have a bunch of points, right? And we want to find a good representation for them. And I actually like the fact that it not interpolates, but it can be converted to occupancy and sign distance field. I think it is like a yeah, somehow a smooth variant of that, right? Where the limiting cases are occupancy. And for instance, on that, if I were to, so if I have a bunch of points, one of the tasks that I want to accomplish is computing surface normals, right? And if I have the implicit field, somehow I know directly the surface normals of that. And I was wondering if, instead of using the regularizer, why don't we just get the non-regular solution? So regularizer on the gradient norm. That's what I mean. And then actually extract the surface normals, as a function of the field. Would that be possible, or would this be a little unreliable?
You're talking about unsigned, because in unsigned,
no. Well, unsigned. I think the unsigned case is not yet covered, but even for the signed case, the question is.
So you mean, like, for example, if you consider this, you take the normal as the gradient of this field.
Right.
Yeah. So definitely, I think you, in some sense, the way I perceive it, maybe it's wrong, but in surface reconstruction, what people used to do is first approximate the normals,
right,
and then the surface.
Mm-hmm.
In this thing, we actually do it directly the surface. So definitely you can take the normals after you reconstruct the surface. Yeah. I don't have anything intelligent to say about it.
Okay, sure.
I do want to point out that a lot of works in the past where the question about you know how to create unoriented field, like you know the normal up to a direction, and now you first make a consistent choice for each normal, and then this is like almost reconstruction.
Yes, that would be the typical classical setting, I would say.
Yeah.
But computing normals is always a hassle. If the point clouds are noisy and everything, right? So I was wondering if the reverse would be a good direction. And
it's a good question to see whether these lead up to normal orientation better than what like classical method.
and I also see, to kind of give my maybe last question for this round is, I see a lot of links. I don't know, somehow I feel like because we are minimizing over U, right? This energy, it's kind of resembled a lot of ideas that people use in optimal transport. So to do the for instance, that get the KL regularity there, this, or entropic regularization and so on. Do you see any, like similar techniques being used here somehow? Because the nature of the problem resembled a little bit. Yeah, it's definitely not the same, and or not even similar, the problem being solved, but
Yeah, so it's an interesting question. I can't say I see immediate connection, except like the obvious thing that adding a small kind of regularizer part makes everything simpler, well-defined, easier to optimize, local minimums. But I think that also is true for many other things, even computing like the pseudo-inverse. But whether it's a good question. I don't know. I cannot comment beyond that for now. But the regularizer here is definitely something that we've seen a lot. Basically, it's like the square norm of the gradient is something that we use in Poisson equations.
Okay. So maybe we ask one round of questions from on the chat. I think there's quite a few questions over there. Okay, so I think so the first question from one audience is that asking about how the inductive bias from phase behave on holes or concave shapes, like donut or circle with Miss arc.
So on a shape with holes,
holes and concave regions.
So if I understand correctly, let's say that the points come from like an annulus, and we want to reconstruct this shape. So the implicit in general, unless you do something special, it's boundaryless surface. That's one thing which is important to say. But topologically wise, it's very flexible. So even in the examples I've shown here, creating surfaces with handles and so on is not a problem. Containing surfaces with holes, meaning with boundary, is a problem. It's also interesting future work for implicit representation. How do we incorporate boundaries into these things? Because zero of implicit functions are boundaryless. Let me see if I have here yeah, so I don't know, maybe here you can see a non-trivial topology. I'm actually not sure, maybe Vincent knows better than me, but I think that this model has some non-trivial topology, like closing a hole with the elephant trunk or something like that. Definitely topology is not a problem for implicit functions. Actually here maybe there is like a complex topology of these lamps. There's like it looks like a Mercedes kind of shape inside. Also the chairs are not trivial topology. So topology is not a problem. Boundary is a problem.
Okay. Okay. So next question, so it's a little bit general. Is that asking the potential of using this combining this with, for example, differential rendering, by optimizing geometry when used in rendering. Maybe you can comment a few words on this.
So what's the question exactly?
So the question is that asking about the potential application of this phase in optimizing geometry, right? So when using in rendering.
Yes. So I think in general, also for differentiable rendering, the question is if you like to incorporate a bias which try to minimize the surface area, whether differential rendering or elsewhere, then you can use it. It's basically, I think this is kind of goes back to maybe one of these messages here that if you want, you can train either SDF and occupancy, but you can go between them if you want to incorporate other constraints. So yeah, I think generally you could use it with whatever you want. I think the main question would come whether the inductive bias that is presented with this loss suits the application in mind. If that's the case, then I would say yes.
Okay, so we have the last question from the audience. So let me just read this. So why have encoder-decoder architecture not been successful in optimizing losses like IGR and phase? We have seen auto decoders and the single thing overfitting work with this. What might be the reason?
So I didn't get it completely. You're saying encoder-decoder was successful or was not successful?
It has been not that right. So why have encoder and decoder architecture not been successful in optimizing losses like IGR and phase?
I think they're pretty successful. So there are work by Matan Atzmon, one of my students, that did a lot of encoder decoders with implicit representations. So I'm not sure. The question is why it's not successful.
Yeah. So basically we have right. So well, the question also basically asking about your opinions, right? So the applications of encoder and decoder architectures in optimizing losses like IGR and phase. So maybe make a comment a little bit on what type of architecture we should use, right, when combining with the theory you presented.
Yeah, so I think the way we usually did it, and I think others as well, it's not only us, also Anders Geiger, I think Vincent did similar things as well, is that we have an MLP that takes us from, this is like maybe in R3, and here we have some latent code. And when you fix, let's call this in phi, and when you fix the latent code, you have an implicit representation, right? So this is our U. And now basically the shapes are controlled with this latent code. You can, so some people like Park et al., the people of DeepSDF, optimize directly those codes. Some people have used encoder to learn these codes from, let's say, point cloud using point net architecture. So these are the type of things. Matan Atzmon did encoder, variational encoder of these, and others did it as well. I don't remember all the citations by heart, but the idea is that once you do that, you have a framework where you have a shape space defined by this latent code, and now you can incorporate constraints like IGR, like phase, whatever you want to these networks, right? So you can add constraints to this function. And I don't think these things are contradicting. You can add them to whatever system you're building. What our experience shows that you can train a family of SDFs from a family of shapes, meaning that when you change Z, you're still maintaining this SDF properties. So it's not contradicting. You can learn a family of SDFs as a function of this input here when you fix Z.
Maybe one interesting thing to discuss is that these methods that use global conditioning latent codes like this one, by which I mean there's one latent code that represents the whole scene, are as Yaron said, constrained to be trained on families, like relatively low dimensional families of objects. So for instance, what would we can train them on ShapeNet. What would not work is we could not take like 60 room scale environments and like learn a space of room scale environments in this manner. And that is still an outstanding problem. And people have been addressing this with this like notion of local conditioning, of having like a hybrid explicit implicit representation where maybe you have a voxel grid that locally encodes these latent codes and you locally condition the implicit representation on these latent codes. And that then does allow you to generalize across much more, or like learn priors over much more complex scenes, but the priors you end up learning are priors that are local. So rather than learning a prior over the whole scene, as with this example that Yaron sketched out, you would be learning priors over like local properties of the scene, like local surface properties and so on. And I think this is a very this is one of the to me at least, that's one of the most interesting questions of like thinking about bridging that gap and like thinking about how could we learn priors over much more complex, maybe compositional scenes.
Yeah, I think it's a very interesting question. We also noticed that it's the generalization of a global encoder with a single Z would not capture like huge amounts of different objects and scenes. And I think it's really interesting. So one direction is definitely what you mentioned. I wonder if there's no, because we know that encoders are pretty general. And so I'm not sure that the bottleneck is global versus local. Maybe something we're doing wrong with our encoders. I don't know.
Yeah, I think that may be the case. Yeah.
Yaron, I was wondering if you actually tested the generalization of this method, not on scenes maybe, but on simple objects, right? Because you have a lot of inductive biases, and do they help you generalize better than other methods?
So here I didn't test it on collections at all. The only thing here is that a single shape you can think about to get point, and you measure on, you can test on areas you didn't see. So that's something in the spirit of this benchmark. But I completely agree that it will be interesting to see. So by the way, interesting follow-up would be you can take a phase-like constraint and add it to the encoder, or something more general, classifier, and maybe that would help you generalize in a different context of implicit representation. So I haven't done that, and I haven't done collections as well here. So, but I think are all interesting questions.
And I mean, coming from the generalization side, I think you also did not finish the convergence to the true SDF, right? Or am I mistaken? What prevents that from happening?
So to be honest, that's so I was surprised. I looked in the viscosity theory a little bit. They have a lot of convergence. I couldn't find, I don't know if someone from the audience or someone knows the answer. For example, the convergence of the SDF in an unbounded domain, like outside the shape, not inside in a compactor, outside. I didn't see any result about that. At least I couldn't find anything. For me, as I said, something that prevents me from proving it in the inside was the fact that these little balls inside those, it's not like, it's like the boundaries are moving a little bit. They're not constant like a Dirichlet problem. So that technically it was a little bit difficult. I think it's interesting. I'm not sure it's worth the effort because I don't know how hard it is. But I would be happy to hear the answer if someone has it. So all I can say now is that it locally behaves, satisfy those viscosity PDE. The global convergence is something that needs a little bit more technical kind of effort.
Okay, so I have a somehow relevant question, quite a high level. Is that do you think this kind of like where you have two losses, you have a weight, right, mu, right? This kind of a combination weight. Do you think this mu can be spatially varying to learn how to combine these two losses? Or you think this rather you have different losses, right? So do you think this can make this like spatially varying, right?
So what do you mean?
So
Like
basically,
maybe
mu depending on the location, right? For example, you can maybe the features of the shape, right? So they at different places they have different characteristics, right? We can use different ways, different combinations of the losses to handle those. So you have two losses, right?
Yeah.
If I remember correctly.
Yeah. So there is this. So I think one one loss comes from the positional constraints.
Yeah.
And the other one comes from, let's say, the minimal surface.
Yeah. Yeah. But the trade-off parameter, right, between these two constraints, do you think this can be varying or can be learned, right? Freedom lambda here.
Yeah. So all I can say is that I know how this lambda should asymptotically behave with respect to epsilon. But I think that also this thing here, the shape of these balls, and actually this is like uniform density on the balls. And I think all these things can be learned. Why do we want to learn? We take a priori, right? Maybe anisotropic balls, maybe we want to learn those. So I think there's a lot of questions here of how to combine those. In general, I think this type of loss better kind of reflect the fact that we want the surface to pass through the points and not that zero out, as I mentioned at some point. So I think if I'm taking your question to the next level, I'm saying not just the parameter, but the entire densities around the points probably should be learned in order to produce good results.
Okay.
Or to improve results, yeah.
Okay, thanks. So then we'll have another round of questions among the panelists and the speaker. A little bit more high level, right? So usually, I think this round we ask you a general opinion about the like learning applied to 3D geometry, right? So what are the fundamental challenges and what will this community will build, right? So I think new representations, right? Implicit representation will have play a very important role here. Maybe we start with Vincent, right? So what is your opinion about this newer representation, in particular implicit representation or right? So for shape modeling, rendering, etc. Okay, we can. So you're muted.
Yeah, I'm having my Zoom is having problems. Okay, can you hear me?
Yeah.
Excellent, good. Yeah, let's see, more high level. I think Yaron already touched on many of the questions that are, I think, relevant here. So I mean, one question really is, at the end of the day, as Yaron said, we are running into problems of how long does it take to fit these shapes, like the training is extremely expensive. So I think one question maybe is, one interesting thing to discuss is like, what are the immediate applications that we could actually, that this will actually become useful for? Like, if we want to represent shapes in this manner, but every time we want to represent a shape, we have to train a neural network, and that is very expensive to do. Is that then a good shape representation? Is that a useful shape representation if it's very expensive to fit it? Although we could probably speed that up, but maybe that's something that's interesting.
Okay, thanks, Vincent. Maybe next with Toga, what is your opinion about this kind of high-level question?
Yeah, so what I'm feeling like when we are doing this type of early work, right? Let's call it like this. This is, one of the works of principles. It's mostly evaluated on some kind of objects, right? The 3D objects, either ShapeNet and something like that. But then we immediately start thinking about the real scenarios where points are noisy, things are not nice, and that we cannot measure. And then robustness becomes an issue, right? So how do we make these things more robust, I think, is an important question. And also, not just robust to noise, but maybe also robust to, for instance, there are a lot of dynamic objects, right? So that I think it connects a little to Vincent's point, that how do we online update those, right? If I have a representation at hand, how can I actually go and insert new things that are coming in the scene and then SDFs are, for instance, bad at correspondence problems, right? Solving correspondences. And this, I think, one of the great parts about this is it's interpolating between, occupancy and SDF. Then maybe it can give us something more, right? For instance, maybe it is easier to solve certain things in one domain and then the others are easier to solve in the other domain. So, for instance, can we get better semantics, and can we get the semantics of dynamic objects in this manner? I think these are all open questions in the context of implicit representations.
Okay, thanks, Tolga. Now let's go back to Yaron. I would like to ask specifically, for example, the potential of this for dynamic objects, and also potentially combining implicit representations and other representations to address more challenging problems. Can you comment a little bit on that?
So I think you're doing great work in that in that space. So I heard several of your talks about combining different representations. Yeah, so I think it basically goes down to the point where each representation or each choice of inductive bias, like in my talk, leads to different benefits. I think combining those things can help us. I think one, definitely like capturing good inductive biases for deformation or time series is also a worthy cause. Incorporating things like deformation energies that we know from graphics are all very interesting. And I think we're probably going to see in the next few years that all those different energies going to find themselves incorporated in systems that learn. I think that at some point it will be interesting really to see how do we make these things really scalable and work. And this also relates to what Vincent said before, in real time and practical, because training a surface for several hours is not practical. So either we're going to find out a quick way to optimize, because in classical method, we were able to optimize stuff, even nonlinear stuff, in minutes, right? Not in hours. Or using encoder decoder, hyper networks, stuff like that to make things instant, at least at deployment. But one of these two routes have to happen in order to make these things really usable, I guess, for reconstruction or deployment of these models.
Okay.
So
thanks. Yeah. Okay. So thanks all. So this is a good time to end this seminar. I think we have upcoming seminars during the summer and in the fall. Okay, so we have people with again with different background, right? So geometry, vision, machine learning, and so on. And really, thanks Yaron for the wonderful talk, and for Vincent and Tolga for this very inspiring panel discussion. We covered a variety of topics. Okay, thanks all for this seminar. Okay.